begin today with a little discussion on the so-called supercritical fluid point. This is the mystical point where a substance loses the distinction of a phase boundary between the liquid and vapor that is in equilibrium above the liquid. So how we can envision this happening is, let me fill a chamber with some liquid of interest and then evacuate the space above the liquid. Then I just begin to heat the liquid, and of course now there will be pure vapor of the liquid, not anything else. There's no air in there or anything else. So there's pure vapor in equilibrium above that liquid phase. And as I continue to heat it, of course, what happens is I get a greater density in the vapor phase because of the fact that I'm getting more and more molecules present in that vapor phase above that. And I actually have a decrease, believe it or not, in the liquid density, liquid phase density as well. And then eventually I come to a point where we will call it the critical point. And there's a certain critical temperature and actually critical pressure. This is important too. There's critical pressures and temperatures. As a matter of fact, these can be derived, if you recall, a long time ago. We looked at inflections in the PV plot curve, and we called the inflection points the critical point for that gas. That will be the point where it's really neither gas or liquid. It's this homogeneous mixture of material, kind of like a fog of, probably reminiscent of when you're in a very hot shower and you get out all the steam in the shower stall that you might envision around you. I would imagine that the supercritical and the critical state of the matter is similar to that. There's no phase boundary delineating a point where a liquid is in equilibrium with vapor any longer once you get to the critical conditions. And you see what we have listed there are the critical temperatures and pressures. Notice the pressures are fairly high, at least for normal things except for maybe helium. They're fairly high critical pressures that are required to get to these conditions. The rest of this lecture is going to deal with the consequences of Gibbs' phase rule. Remember this phase rule that Gibbs is attributed to. It is a very simple equation and reads F equals C minus P plus 2. F being the number of degrees of freedom in the system, or what we can think of, what I mean by that are the controllable parameters that you can place on a system. We'll explore more of that as we go along here. What is the C? It is the number of components, how many actual substances are present in the particular system you're studying. What is the P? That's the number of phases which are present in the system. Now, we must be a little bit careful. This is not the states of matter present. States being pretty much solid, liquid, or gas. We can also throw plasma in there if we would like. But phases are actually uniform throughout, and you can have multi-phase states, for instance, and very obviously what those would be things like mixtures of coal with diamond. Those are two different solid phases, the way the carbon atoms are packed in them. You can have oil and vinegar. That is a liquid state, but it is a two-phase liquid because of the difference in intermolecular force between the materials. They have better attraction for each other than they do well, as a matter of fact, to get technical, the polar molecules have more attraction for each other than they do for the non-polar molecules. They clump together and by density considerations separate into their own layer or phase. Okay, so that's the basic premise of what we mean by a phase. We'll explore that again, as I said, the rest of this lecture. All right, so let's begin by looking at a pure substance. That means C is 1. And let's go in a single phase region for any pure substance. So I'm going to assume one phase, P1, one component, C1, so then F is equal to 2. Now here's what the implication of that is. You have 2 degrees of freedom, which means you have 2 controlling parameters. I can independently vary the pressure and temperature of the substance and still remain in a single phase. So I can move horizontally and vertically in the mixture anywhere around in the region, as long as I don't get near the so-called phase boundaries. The phase boundaries are delineated by the regimes where you see the line separating the two different components. Notice there's a solid gas phase boundary, solid liquid phase boundary, and a liquid gas phase boundary in this particular mixture. Now, believe me, what you can see if you're a material scientist, there can be fractured pieces of that solid phase. It could be fractured up into several different regions for the different types of packing schemes that solids can enter into, and they would each have their own little pressure and temperature areas where those are the favored forms of that particular solid. Not in a one component. Anytime you have a one component plot, there's only going to be one liquid phase. All single components are completely miscible with themselves. Okay, let's make sure we're very clear on that point. If you have a one component system, you must have a single phase for that system, liquid phase for that system. If you have a one component system, you can have multiple phases of solid for that one component. We call those allotropes. There are 3 popular allotropes of carbon: diamond, fullerenes, or graphite forms of diamond. So you could fragment the one component solid phase region for carbon into 3 different sections in that. There would be phase boundaries between the sections as well, and there'd be lines delimiting the regions between the 2. Okay, so in conclusion, when you have one component, one phase regions, F is equal to 1 minus 1 plus 2, or there are 2 degrees of freedom, and we choose those 2 degrees of freedom to be the pressure and the temperature. Now, there's no controlling, let's be clear too. In a case like this, there's no controlling N, the number of moles. It doesn't matter. The number of moles is not a controllable parameter to define. Just by piling more water in at a certain temperature does not make you approach the phase boundary. So the controllable parameters that are at least most obvious to us in this instance would be the pressure and temperature you expose this one component substance to, and you can move around 2-dimensionally and remain in a solid phase, in a liquid phase, or in a gas phase, as long as you are away from the phase boundaries. Now let's explore a one-component, two-phase region. What that means is when 2 phases of this one component are in equilibrium, you are on the line which separates the 2 phases of interest. You can be along the solid gas line, the solid liquid line, or the liquid vape gas line. Let's focus our attention to the liquid gas line for a moment. Now here F is equal to, again, C minus P plus 2. C is 1, P is 2. So I have 1 minus 2 plus 2. F is equal to 1. There is only 1 degree of freedom. So the implication here is I can choose one value and then the other is fixed, and I do mean fixed. Now again, let's focus our attention to the liquid vapor phase boundary. What this means is if I slide along and choose a particular temperature that I wish to examine the liquid and vapor, or liquid and gas in equilibrium, then I have no choice but to go up to the equilibrium phase boundary and bounce over to the pressure curve and identify the vapor pressure that that liquid is in equilibrium with at that temperature. Okay, now let's get this straight. Remember, this is a one component phase dot. We're talking about a one component application of the phase rule. And it's a one component application, meaning there's no air in the chamber. When I say liquid and gas are in equilibrium in this regime, it has to be the liquid of the one component and the gas of the one component. Otherwise, you'd have to put a different number in for C. If C is going to be 1, then F is 1 when P is 2, and we're talking solely about the vapor phase of that pure component in equilibrium with the liquid phase of that pure component. Okay, so in other words, if you pick a particular temperature, there is only a single vapor pressure of that liquid in equilibrium with the liquid at that temperature. Or vice versa, if you chose a particular, you wished to know that the vapor pressure of the liquid was at a particular value, then you would slide along and come to the curve and bounce down. There's a single temperature where the vapor pressure reaches that value. Now remember, the normal boiling point of a liquid is when its vapor pressure reaches sea level atmospheric pressure, or when it reaches 760 millimeters of mercury. So if you want to identify where the boiling point of the liquid, the normal, make sure clear, normal boiling point of the liquid would be on this curve, I would go up the pressure axis till I hit 1 atmosphere, bounce over to the liquid gas boundary, and then bounce straight down, and the temperature that corresponds to that point must be the normal boiling point of the pure liquid. Now go to our pure substance, again with C equal 1. And now let's look at the point where 3 phases are in equilibrium simultaneously. That would be P equal 3. So I have 1 minus 3 plus 2, or I get F equals 0. There are no degrees of freedom once you have a pure substance 3-phase mixture. What that means is that represents a single point on this PT curve. You have no degree of freedom. It only comes at a single point, and at that point there is a fixed P on the ordinate axis, there's a fixed T on the abscissa axis. So there are definite triple points for each pure substance with a definite pressure and temperature. You can't vary either of those components if you want all 3 phases, solid, liquid, and vapor, in equilibrium to one another. Now, there can also be triple points between other phases of a solid, things of that sort as well. But in this particular case, we're not going to talk about a multi-phase solid that we might be dealing with. That's something for a material scientist to worry about. Our most familiar phases are the states, and those states are solid, liquid, and gas. So the triple state is a triple phase point where there are no degrees of freedom. And for instance, as I show there, for water, its triple point is right about 0 degrees C, or 273.16 Kelvin. And at the paltry pressure of 0.00604 atmospheres, way down there, only like a single torr or so of pressure, a couple torr of pressure. The triple point for CO2, you can see, is at least in pressure-wise is dramatically different. About 4 orders of magnitude, or 3 orders of magnitude difference in pressure anyways, to 16.8 Kelvin and 5.11 atm for the pressure. As we say here, even though it's endothermic for the vapor to, from liquid to vapor transition, so you have to input energy to invoke that transition, it's still a spontaneous process at a wide variety of temperatures, And this is in satisfaction of the entropy requirements of the material. So the point would be this: at a given temperature that you specify, a material is dictated by nature to possess a certain amount of entropy or randomization to the material. So the degree of randomization of the material at that temperature is going to be a function of how the molecules interact with one another, and in some regard that would be whether or not they're in the liquid or vapor phase. So you can think of it as if molecules will need a certain number of them present in the vapor phase along with those in the liquid phase to add to their entropic requirements to satisfy the degree of randomization they should have at a given temperature. When you raise the temperature, you raise the amount of randomization that the system must possess. So naturally, by releasing more molecules into the vapor state, that increases this degree of randomization and allows a substance to maintain the entropy quota it should have at that particular temperature. Okay, now what is interesting about this is let's now mix, as we will very soon, two non-volatile liquids and think about, let's mix two volatile liquids, meaning liquids that have vapor pressure. Well, then they have requirements of, due to their mixing, that there's a change in the entropy of that system. We're going to explore this later on in terms of the ramifications it will have on the number of molecules which escape into the vapor phase above that. But now let's note that what we can do is we can evacuate a chamber, again, as we did in the critical assessment earlier in the first slide. Now I'm going to put some pure substance in that chamber, here maybe water, and then I will soon establish an equilibrium between the water in the vapor phase and the water reconstituting and being captured back into the liquid phase. So at equilibrium, I have H2O vapor and H2O liquid in some balancing process between the two. As I increase the temperature again, this increases the entropy requirements of the process. As a matter of fact, you can think of it thermodynamically as well with regard to the fact that now the molecules are at a higher temperature, have more motion. They have more motion, they're moving more dramatically. When they're moving more dramatically, the degree of their intermolecular force is compromised so that they're not so sticky and more are capable of escaping to the vapor phase. So the vapor pressure will naturally increase as I raise the temperature of the sample, and then finally that vapor pressure will reach the point of the pressure being supplied downward upon that liquid. And when the vapor pressure matches the external pressure that is supplied to it, we call that the boiling point. When it reaches, if it happens to be that it reaches the point where it is being pushed back upon by 1 atmosphere of pressure, we call that the normal boiling point. If it is being pushed back upon by 1 bar of pressure, we call that the standard boiling point. Let's consider the behavior of what we will call partially miscible liquids. Now, miscibility means they mix in any proportion. But when I have a partially miscible liquid, it means it will mix in any proportion only at given certain temperature requirements. So let's have some pure liquid A with B that I dump together into one beaker. And what happens initially for the partially miscible liquid is at the ambient temperature of the room, they separate into a two-phase state of liquid, meaning there is a less dense phase floating on top of a more dense phase. Let's suppose that B is a less dense liquid than A, so the layer on the bottom will be primarily composed of the more dense material. Now, don't think that they're completely immiscible. there will be some amount of B homogeneously dispersed among the A in the lower phase. And likewise in the upper phase, there will be some amount of A homogeneously dispersed among the primary domination of B in the upper phase. However, there still is a distinct density difference between the two phases of this liquid state, so gravity will compel them to separate with a phase boundary that is discernible between them, typically due to the difference in index of refraction of the two phases. Now, if the two phases have very similar index of refraction, they will bend light passing through them to much the same extent, and you won't be able to discern or differentiate by looking at it that there actually is a phase boundary in some instances. Now, sometimes color can help do this, or shining light through it. You can focus a light beam through it. You can see where there's an inflection to the light beam that can help to identify this. But if you have a nice, powerful difference in index of refraction, light will be bent to different degrees when it enters one layer compared to the other, and you will in that instance have a very discernible phase boundary that you can note between the two phases. Let's look at the phase diagram for this two-component, one or two phase liquid that we described on the previous slide. And let's look at how we can interpret it, because there's some really interesting interpretations that you can glean from the phase diagram. The curve for a two-component, one or two phase liquid typically has this inverse parabola look to it. And remember, what the inverse parabola actually represents is a phase boundary between the two values. All right, now let's get clear here, first of all, about what's going to go on when we look at Gibbs' phase rule with regard to this, and we'll try to make sense of this inverse parabola. Okay, F is equal to C minus P plus 2, as we did before. Here, I have a two-component mixture, mixing two liquids together. And let's go to when they completely dissolve miscibly in one another. And I have a single phase. So F is equal to 2 minus 1 plus 2. F is equal to 3. There are 3 degrees of freedom in a two-component single-phase mixture. Now I have 3 things I can control, as compared to before when I had a single-component, single-phase. I only had 2 controllable things. Before I chose the pressure and the temperature. Now I have 3 things to control. And it's pretty simple to add the third thing that can be controlled. I have pressure, temperature, still controllable, but now I'm going to add in mole fraction, or some way. It doesn't have to be mole fraction. It could be some way to measure the relative composition of the two phases. Now, I'm not going to use molarity ever. Why would I never use molarity? Because molarity is not independent of temperature. Mole per liter, mole per volume ratios can change with temperature. If I'm going to do this correctly, I should use a concentration unit that is temperature independent, certainly. Now, there could be several of those. There could be mass percent would be one that you could use. Mole fraction would be one you could use. Molality would be one that you could use. Parts per million, parts per billion you could use, but you certainly couldn't use molarity, even though it's a more popular choice among many factions of chemists. So I'm going to choose my third degree of freedom to be the mole fraction of the particular sample. So now if I want to look at two-dimensional plots, now I could make three-dimensional plots, but they're kind of messy to look at. I prefer two-dimensional plots. I'm only going to be able to plot 2 of these degrees of freedom. Now I could choose a mole fraction and then examine the pressure-temperature relationships that they have. I could choose a particular temperature and have a pressure mole fraction relationship of interest. What I've chosen to do here is much more typical. I'm going to set the pressure to be room pressure, which it is. It's what there is. There's room pressure pushing on my beaker of these two components. And then I'm going to look at how the mole fraction and temperature vary. So on the abscissa, I'm plotting mole fraction of one of the components. Now notice, again, I only have control of one of the I'm only going to be able to control one of those because I have two remaining degrees of freedom. I don't have control of mole fraction of B, but I kind of do implicitly because, of course, XB is equal to 1 minus XA. So I always immediately know my XB value simply by looking at it as 1 minus XB, or XA, because, of course, the idea of mole fraction is that XA plus XB equals 1. So my 2 degrees of freedom that I'm going to be interested in here, because of the fact that when my partially miscible liquids, as I increase the temperature, there comes a point where they're completely miscible. So I study the phase boundary between various components of this, and I come to this particular curve where I'm now going to plot temperature versus mole fraction XA. Those are my remaining 2 degrees of freedom after I choose constant pressure as one of my stipulated degrees of freedom. F prime is 2, down from F equal to 3. Now again, what does this mean? The 2 degrees of freedom being the temperature and the mole fraction of A, I can move horizontally and vertically independently in the one phase regions of this 2-component partially miscible liquid curve. I can vary the mole fraction and the temperature independent and still remain in the one phase liquid region above the curve. Okay, only above the curve does this work. So again, let's be clear on this. I have independent motion only in the region above the curve, not under the curve. Because let's now analyze Gibbs phase rule under the curve. Under the curve, I have 2 components, but now I have 2 phases. So C is 2 and P is 2, so F equals 2 minus 2 plus 2, F is equal to 2 under the curve. Now again, if I specify pressure of the room as being out of the window, it's a controlled pressure of 1 atmosphere in the room, I only have F prime equal 1 under the curve. What does that mean? If I choose a particular mole fraction of A, then the temperature at which the 2-component mixture will have that mole fraction is set. If I choose a particular temperature, then the mole fraction of A in the component is set. Now though, let's look carefully at what happens if I choose a temperature. If I choose a particular temperature in the regime where I'm still going to be under the curve, I will intersect the phase boundary at 2 points. This is so subtle, but it's really cool and interesting and important. If I go horizontally across, I choose a temperature where I wish to examine the properties of my partially miscible liquids. When I'm at temperatures below a certain critical temperature, then 2 phases are possible. Notice there's a temperature above which I'm always only going to be in a 1-phase liquid. Now, again, let's go to a particular temperature where I intersect the curve at 2 points. What we are finding are the 2 points representing the mole fraction of A in the 2 phases that will exist independent of one another in that liquid state. So you'll notice at the T I've chosen here, I have an XA1 of relatively low mole fraction of A. That is the amount of A dissolved in the B-rich layer. As a matter of fact, from 1 minus XA1, I will get the mole fraction of B in that particular mixture, in the B-rich layer. So, okay, let's slide over on the horizontal T-line to the right. Again, I have a second intersection of the phase boundary. And if I bounce down to the mole fraction line at that particular temperature on the phase boundary, I get an XA2. That is the mole fraction of A in layer 2. Notice it is much richer in A than it is in B. This is the A dominant phase in the two phases. So I know the mole fraction of A in phase 1, or in the upper phase. I know the mole fraction of A in the lower phase. And of course, because of the relationship of 1 equals XA plus XB, I know the mole fraction of B in the upper phase. I also know the mole fraction of B in the lower phase as well. Look at the true utility of this phase diagram. Let's suppose I prepare a mixture of partially miscible liquids that has mole fraction YA. So I put, I put YA equal 1/3, it looks roughly like. So there's twice as much B as A, so that when you put the mole fractions together, I get a YA of 1/3, essentially, is what it looks like. Now I choose a temperature that I wish to examine how or whether or not this will separate into two phases or whether it will be a single phase. Now, so what I do is I slide along the XA curve till I come to the particular mole fraction YA, and I move upward until I come to the experimental temperature T, at which I have decided I'm interested in the mixture. Notice that the temperature I've chosen is such that I am underneath the curve. So I'm in the two-phase region of the liquid by being under the curve. So my liquid will definitely separate into two phases for this YA mixture that I prepared. Now, as a matter of fact, I want you to note that that T is what we call a horizontal tie line. As long as I specify T, I will have the same proportions of A in the upper and lower phases, no matter what YA I choose. Definitely at the temperature I chose, the XA component in phase 1 is given by XA1. The XA amount mole fraction in phase 2 is XA2. This is true no matter what YA is at that temperature. Notice all I would be doing is sliding the vertical dashed line along the horizontal dashed line. But what does become different when I slide YA to the left or right is the so-called lever rule. And what the lever rule states is I can measure the distance L1 and L2 from YA to the intersection of the curves on the left and the right. Notice if I move YA around, the only thing that will change is it's not XA1, it's not XA2, but it is L1 and L2. And what was discovered, I'm not sure if it was by Gibbs or by others, is that you can now measure this lever rule kind of like a seesaw. It's telling you the relative proportion of the amount of the two phases that will be present. The bigger the L2, the less phase 2 there is. The smaller the L2, the more phase 2 there is. So it's kind of like a seesaw point. If that intersection point so that L1 and L2 are the same length, that would mean the size of phase 1 and the size of phase 2 are about exactly the same. The one's about an inch thick, the other one will be probably about an inch thick. It might be a little bit different based on how they're packing, but the relative proportion of the components will be the same based on that lever rule. Now let's slide YA to the left a little bit. Notice L1 gets smaller and smaller and smaller. And by the seesaw effect, that means that the amount of N1, the amount of A in layer 1 is becoming greater and greater and greater. So the amount of layer 1 is becoming much larger as I slide YA to the left. Moving it the other way, the amount of layer 1 is getting smaller and smaller and smaller until I get all the way over and make YA equal to X2, XA2, then there is essentially no more layer 1 left. When L1 goes to the whole way across, that layer 1 goes to 0. As L2 goes to 0, layer 2 goes to all of the sample, or the pure sample. Okay, so again, the lever rule itself can be thought of as reading N1 L1 equals N2 L2. Then if I want to solve for the relative amount of phase 1 compared to the relative amount of phase 2, I would just say N1 is L2 N2 divided by L1. And again, if L2 equals L1, N1 equals N2, there's about the same amount of material in each of the two phases of the separated liquid. Let's do a little exercise with a partially miscible liquid problem here. Suppose at 25 degrees C, I mix 2.4 moles of water with 1.15 moles of phenol. That's of course a benzene ring with an alcohol group on it. And I have this phase diagram known for this partially miscible two-phase system, or two-component system, sorry. And I go to 25 degrees C, and I want to know what is the mole fraction of each phase, and I want to know what is the particular relative proportion of the two phases. Well, the mole fraction of phenol at that particular number of moles mixtures would be 0.324, about a third of the way over. And then if I go up to 25 degrees C, go horizontally across, and I bounce down to the phenol mole fraction curve, I'm finding that in phase 1, the mole fraction of phenol is about 0.12, and in phase 2, the mole fraction of phenol is about 0.78. Then when I look at the relative size of those two layers, or just like I measured how big one layer is compared to the other, what I would find according to the lever rule and saying that L2 is about twice as big as L1, then I would get N1 is equal to L2 N2 over L1, and I'm going to get N1 is about 2N2, or the layer 1 will have take up twice the separatory funnel as will layer 2 will in the separatory funnel if I'm doing this in organic lab. Let's now look at a two-component liquid vapor phase diagram. They have the appearance very typically that you see here to the right, and we'll talk a little bit about the curve in a moment, but let's first examine two-component liquid vapor phase regions on this curve. Let's look at the regions where there's vapor only, or actually where there's liquid only. And so there will be no vapor in equilibrium with the liquid, or in the vapor region there's only vapor, there's no liquid available. It's two components, C is equal to 2, P is 1, so F is 2 minus 1 plus 2, or 3. There are three things that I can control in a two-component liquid vapor phase, single phase region. So I'm going to again state we're in a laboratory where the pressure is fixed. Now I could have stated the temperature is fixed and look at P versus XA, but I'm going to go with fixed pressure, vary the temperature, more easily for me to control in my laboratory environment. And my other variable is going to be one of the mole fractions. Now, of course, the other one is, of course, it's not an independent variable. So once I specify XA, I know XB because 1 minus XA equals XB. So it is not an independent variable at all. So once I specify in this one phase, two component region, 3 degrees of freedom, throw out the pressure, I have temperature and mole fraction can be independently varied. So now I'm going to go to my plot. It is a plot of T versus XA. And of course, when XA is equal to 0, I have pure B. So the intersection with the T curve at that point must be the boiling point of pure B. So notice then from that intersection on the left side ordinate axis, I have TB star, which is the boiling point of pure B. Now if I slide along to XA equal 1, of course there is no B in that mixture, and I have the intersection with that ordinate axis being TA star. So TA star is the boiling point of pure A. And notice what we can tell from this graph is that TB of A is a higher value than TB of B. So it takes more input temperature to boil B than it does to boil A. What is that also saying then? B is more volatile than A, right? B escapes easier, exerts higher vapor pressure than A. So therefore, if B exerts higher vapor pressure than A, its external pressure will reach 760 before A will, and it will boil before A will. So B is certainly a more volatile component than A, based on the fact that TB for B is lower than TB for A. All right, now going back to the analysis of the one phase, two component regime here, I got F equal 3, and when I throw out the pressure, I get F prime equal 2. That means I can move horizontally and vertically independent in the one phase regime, either at the bottom where I'm in a one phase liquid or at the top when I'm in a one phase vapor. I can vary the mole fraction of A independent of the temperature and still remain in the one phase region. Okay, now let's go to the two component two phase region where liquid and vapor are in equilibrium with each other. So the liquid will be exerting vapor pressure in these regions. C is 2, there's two components, but now P is 2, there's a liquid and a vapor phase. So F is 2 minus 2 plus 2, F is equal to 2. I have two controllable parameters. Once again, just like I have done in the previous example, I'm going to throw out the pressure. I'm going to do it in a laboratory where I'm going to set the pressure to be a value. That's a controllable parameter, but it has to be taken care of. So I have only one remaining degree of freedom. I can look at it from one of two perspectives. I can choose a temperature. Okay, first of all, let's point out, I am now in the region between the upper and lower curves. The upper curve represents the one phase vapor. The lower curve represents the boundary for the one phase liquid. In between those two curves, I have a two phase liquid vapor equilibrium. Now notice, if I choose a particular temperature, I will get two intersection points. I will get an intersection point with the vapor boundary. I will get an intersection point with the liquid boundary. And just like we saw on the previous example, these intersection points will tell me the mole fraction of A in the vapor phase and the mole fraction of A in the liquid phase now. We won't call them phase 1 and phase 2. We'll call them actually what they are. They are the vapor phase, which is the left, the upper curve, if you like, and the liquid phase boundary, which is the lower curve as you like. Now remember, I just a moment ago stated that the component B was more volatile. So you will notice always in the vapor phase, there is a lower mole fraction of A than there is in the liquid phase. The liquid phase is richer in the less volatile component. The vapor phase is always richer in the more volatile component when you have these mixtures. Now notice, once I choose a temperature, the proportion of A in the vapor phase and the proportion of B in the vapor of B in the vapor phase are fixed, and also they are fixed in the liquid phase as well. Now, what can then vary is the amount of vapor compared to the liquid, as we will see on the next slide, because we will once again introduce a way to tell which of the two phases is more predominant based on the amount of A I have placed in the mixture. Let's now look at evaluating particular mole fractions of A at temperatures within the two phase region. And so let's prepare some particular value of the mole fraction of A that we call YA, and we evaluate it at temperature T1. So I slide across the mole fraction axis till I come to the particular mole fraction I prepared, bounce up till I intersect the horizontal line corresponding, we call that again a tie line, the tie line which connects the vapor-rich phase and liquid-rich phase boundary is going to be independent of YA. Notice at the temperature that I choose, there's only a certain mixture of A in the vapor phase. There's a certain mixture of A in the liquid phase. What will change is the relative proportion of the size of those phases. The amount of A in each does not change at the temperature. The relative size of the particular phases will, as I slide YA to the left or right, because what I'm going to then change are the two levers that balance relative to that point of intersection, L-vape and L-lick. Those are my two levers, if I like, again, balancing for a seesaw. If the length on the L-vape side is the same as the length on the L-lick side, that means I'm balancing exactly in the middle, and the relative proportion of the two components will be exactly the same. Here, what I note is that L-lick is shorter than L-vape, and I'm claiming it's about 2.5 times the size. L-vape is about 2.5 times the size of L-lick. So, so there's about 2.5 times as much of the liquid phase than there is the vapor phase because of the slanting of the lever towards a shorter liquid L. That means there's more of the liquid L phase available at that particular temperature. Let's prepare a mixture of components of a certain mole fraction we'll call YA. So we know where YA is on the curve, and let's say I started at a very low temperature and I begin to heat this mixture of YA. At first, it's a single phase liquid. As I heat this mixture of two components, I remain in the region under the bottom curve. That's the single phase liquid region. As I continue to raise the temperature, I move vertically at that particular composition. Vertical motion on a phase diagram of this type is called an isopleth. So my vertical motion along the isopleth is to move upward in the single phase liquid regime. Suddenly I get to a magic temperature where I intersect the phase boundary where we begin to have equilibrium between liquid and vapor. to find the composition of the vapor at that boiling temperature of YA, I go horizontally across to the temperature on the ordinate axis and find the temperature at which that composition of liquid YA will boil. I also know the composition of the vapor phase at that time, at that particular temperature. I look at the intersection of the pure vapor curve, bounce back down, and I get a value of XA1. That will be the mole fraction of the first drip of vapor which appears when I have equilibrium between the liquid and vapor phases. Now, of course, we note that the vapor phase is much less rich in A than the originally prepared mixture of components. Of course, what that means is that it is richer in B, and of course that's because B is the more volatile component. Notice TB star is lower than TA star because the boiling point of A is higher, it is less volatile, the vapor is richer in B. So as the vapor becomes richer and richer in B, that means the remaining liquid becomes richer and richer in A. As you continue to heat the liquid sample, it will boil at higher and higher temperatures as you slide along the bottom phase boundary. So continuing to heat it depletes it quicker of the B than it does of the A, because more B is in the vapor than is A in the vapor. So you're sliding along the bottom curve and you gradually increase the temperature of the boiling as the liquid gets richer and richer in A as you move along that curve. Now you can find at that move to a new temperature, you can find the vapor phase composition of A and of course, therefore the vapor phase composition of B by doing the horizontal tie line. A tie line is the horizontal line connecting the two phase boundaries. I will know XA in the liquid phase, I will know XA in the gas phase. Always XA in the gas phase is lower than it is in the liquid phase because it is less volatile. Now, as I continue to heat and continue to heat, eventually I will get to the elimination of all the B from the mixture, and the last drip of liquid will boil at the boiling point of pure A because all the B has been driven out. Let's look at something that's very familiar to us, I hope, from organic chemistry, and that is the process of distillation. Here I'm preparing a mixture of two liquids, A and B, and in the diagram I'm showing to the right, A here is more volatile than B. Again, how do I know that? When XA is 1, or when I have pure A, the intersection temperature to the curve, if you slide straight across, is a lower temperature than when XA is 0, or when XB is 1. When I have pure B, I boil at a higher temperature based on the intersection of the vapor-liquid curve to the B axis, if you like. So A is a more volatile liquid than B, according to the appearance of this diagram. And the same ideas are true that we talked about on the previous slide. Below the bottom curve, you have a pure one-phase liquid. Above the top curve, you have below the bottom curve, you have a one-phase, two-component liquid. Pure is not really the right word. One-phase, two-component liquid below the bottom curve. Above the top curve, you have a one-phase, two-component vapor. Intermediate, or between the two curves, you have a two-phase, two-component mixture of liquid in equilibrium with vapor. Okay, so I prepare a solution of mole fraction XA1. Now notice, XA1 is not very rich in A at all. It has very little A. It's probably got about a mole fraction of 0.2 or so, maybe even a little less than that, 0.15 mole fraction in A. So it's very rich in B. So I heat this up, and at first I'm marching up the isopleth. Remember, isopleth is the vertical line. I remain in the one-phase regime for a long time because, remember, again, this is rich in B, rich in the more volatile component. So I have to march very high in temperature to get this to begin to boil. As it begins to boil, I can go along the tie line and note that, of course, the vapor that is appearing is richer in the more volatile component. The vapor has mole fraction of A of XA2, which is way greater than the mole fraction of the vapor or of A in the original mixture of liquids. So I got this rich vapor, richer in A, being boiled off, and if I send that through my distillation device, that vapor can be condensed. When I condense that vapor, I again fall straight down along the isopleth down to the XA2 axis. So now let me heat that liquid that I condensed, and it will, that has mole fraction XA2, richer in the more volatile component because it was harvested from the vapor. I heat it until it intersects again to the two-phase region. The vapor which comes out when heating liquid of mole fraction XA2, the initial vapor that appears has mole fraction of A of XA3, much richer in the more volatile component A than it is in the B. And again, if I condense that vapor out, I will have liquid of mole fraction XA3. So I'm making it richer and richer in the more volatile component by the more and more steps of the distillation process I go through. These are called the theoretical plates, or if everything works perfectly, how many times I will have to redistill this until I have remaining only pure A as a result of the distillation process. Again, if I condense the vapor of mole fraction XA, then heat it back up, it will begin to boil at a lower temperature since it's richer in A, and the vapor that appears will have mole fraction XB, and I can then condense that and get a much richer distillate as a result of that process. Again, this should be very familiar to us all from our organic chemistry practices. About another concept you probably introduced in your organic background, and that is what is known as the azeotrope. The azeotrope is, again, a mixture of two components, typically. We're going to mix two components together, and there will be a region underneath the bottom curve where I have a one-phase liquid. There'll be regions above the top curve where I have a one-phase vapor, two-component one-phase vapor, but because of the nature of the interactions between A and B, this curve will exhibit either a maximum or a minimum. Now, there will be a maximum if the A-B interactions are favorable and they reduce the vapor pressure of the materials, which raises the boiling point. So if A and B are sticky towards one another, they have intermolecular forces that make them prefer to stick to one another, then you'll have to, that will lower their vapor pressure, and you'll have to put in more temperature to get them to the boiling point. We call this a high boiling azeotrope. If you see an azeotropic curve which exhibits a minimum, that's stating that the AB interactions are repulsive compared to AA or BB. And when they're repulsive compared to AA or AB, then they're not as favorable to be in the liquid phase as they are to be in the vapor phase. So the vapor pressure of the mixture is elevated compared to vapor pressures of the independent things. And there will be a minimum in the curve, or we call this a low boiling azeotrope. Now notice at the azeotropic mixture of where the maximum or minimum arises, there's a particular mole fraction of A, Ya, for that azeotropic maximum or minimum. And if you prepare the azeotropic mixture, when it does begin to boil, notice that there's no tie line connecting the two phase boundaries. The azeotropic liquid mixture will boil with the same composition as the azeotropic vapor composition, whether it is a high boiling or low boiling azeotrope. Now the problem with these is that you can get trapped on one side of, particularly if we have a low boiling azeotrope. You can only distill and purify your mixture to the azeotropic limit, because the vapor phase in the minimum boiling azeotrope, the vapor is always getting richer towards the azeotrope. Notice on the curve on the right, if I take and heat Ya on either side of the azeotrope, the vapor phase is always pointing towards that azeotropic value. So now if I do several theoretical plates where I boil, collect, and condense, and boil, collect, and condense, the best I can do, whether my Ya is toward the left side or whether my Ya is toward the right side, is to move towards the azeotropic point. This slide is just expounding on the point I was making on the last slide. Here again, I have this so-called low boiling azeotrope. And if I prepare a solution of composition 3, which is exactly of the azeotropic proportion of A to B, and I heat it on the isopleth below the curve, I will just come up finally to the point where I have vapor of exactly that same composition at the azeotropic point. Notice this is the minimum boiling point of the mixture. A low boiling azeotrope, when I'm at the azeotropic mixture, that'll be the lowest temperature possible to boil any mixture of those two components. Now let me move to my starting composition on either the left or right hand side. Let's go to the left starting point first. Very rich in B compared to the amount of A. As I heat, I get richer in A for the vapor, and I collect and condense, I get richer in A for the vapor for that theoretical plate, and I continue to do this, but the best I can do is converge to the azeotropic limit for my distillations. Same thing is true if I go to the right. So I'm beginning with a mole fraction that's rich in A and minimal in B. Now, when I boil that liquid, the vapor gets richer in the B than it does in A. So my theoretical plates take me down in A composition to richer B compositions, and again, I end up at the azeotropic limit after I am able to distill this liquid out. Let's instead look at a so-called high boil azeotrope. This is where the azeotropic mixture has the highest boiling point, higher than either pure A or pure B, as you can tell by the peak of the curve. So the azeotropic mixture would be the mole fraction of A, which gives me that maximum in the curve. Like, once again, above the top curve is a one phase vapor, two component mixture. Below the bottom curves is a one phase liquid, two component, and the two little bunny ears on the left and the right, in those regimes, you have two phase, two-component liquid vapor equilibria, but they straddle the high boiling azeotropic point. So if I have a starting composition to the left of the azeotrope, in this case, you'll notice that the vapor gets richer in B. I'm moving to the left on the axis, so I'm getting richer in B components. If I condense that distillate out, it will be a liquid richer in B. If I heat it up, notice its vapor continues to get richer in B. So I can, on the left side, continue to distill with various theoretical plates until I end up with pure B. Now, if I prepare a mixture to the right of the azeotropic mixture, notice that in those instances, the vapor phase is becoming richer in A, as I'm on that side of the phase diagram. So if I condense the distillate at that point, it will be a liquid that has richer A. Heating it back up, its vapor becomes even richer in A, so I can establish several theoretical plates of distillation to purify my A if I have composition to the right of the azeotropic for this high boiling azeotrope. Let's look at the appearance of a liquid vapor phase diagram when you have partially miscible liquids this time. Now it'll have the appearance that we see on the diagram below the title. Let's first turn to the F prime equal 2 regions. Now remember, two components, this is regions of one phase. So what I should get is F is equal to 3 in those sections. There are 3 of them on the graph. And what they represent then is regions where you have multiple variables which you are allowed to twiddle with and still remain in those regimes, as long as you're away from the boundaries. Again, what we're going to do is specify pressure as being removed. So I'm going to look at temperature, mole fraction as my two F primes. And I can move two-dimensionally, meaning I can change the temperature and still have varying mole fractions, or I can change the mole fractions at various temperatures, as long as I'm away from those phase boundaries. Those are the areas to the far left, to the far right, and up above the curves. In the far left, we notice it's a one-phase liquid with B as the solvent. To the far right, it's a one-phase liquid with A as the solvent, little b mixed in there with it. And up above, it is a one-phase vapor where I have both components present. Now, then there are 3 F prime equal 1 where I have 2 components, yes, but now I have 2 phases in all 3 of those regimes. Now, technically, F is equal to 2 in those regimes, but again, I'm going to specify pressure, remove it from the list. So F prime, the remaining degree of freedom is 1, meaning if I pick a mole fraction, there will be a set temperature at which that is possible, or if I pick a temperature, there will be a set mole fraction in each of the 2 phases in equilibrium. So let's look at those 3 F prime 1. The bottom F prime 1 is the 2-phase liquid zone. So there are certain temperatures and mole fractions where you have 2-phase liquid. You can put a tie line across at a given temperature, and it'll tell you the relative proportion of A in the 2-phase liquids. One of them will be richer in B, one of them will be richer in A. The relative amount of those 2 phases could be gleaned from a lever rule. So if you're at a particular YA right in the middle of those 2, you have about equal amounts of the 2 phases of each liquid. And if you're closer, say, to the A rich zone and far away from the B rich zone, you're going to have way more of the A compared to the B, depending on the length of the lever to the left or right of that particular isopleth of composition up to the particular temperature of interest. Then let's look at the 2 bunny ears up above. I have an F prime 1 liquid vapor equilibrium where I have richer B in the liquid compared to the A, and I have an F prime 1 where I have richer A liquid above in equilibrium with vapor. Again, tie lines will hold connecting the two regimes across in either of those, as we will see. Okay, this series of statements you see here demonstrates what happens if I prepare a mole fraction XA1 and begin to heat it. So first, if I take my XA1, as we say, and heat it up to temperature T1, it's going to be a two-phase liquid at temperature T1, and you slide across the tie line at T1 from XA1 and find the mole fraction of A in the two components. Notice one very rich in A, one very rich in B. Now notice from the lever rule, there is very little of the A rich liquid phase compared to the B rich liquid phase. The lever is much, much shorter towards the B, so that means there's way more of the B. There's probably over 10 times more of the B liquid phase than there is A liquid phase based on the difference in disparity of those two levers. So I finally continue to heat it up to T2, and where I intersect T2, I'm only in a one phase rich in B zone. At temperature T2, I no longer have two liquids in equilibrium. I only have one liquid. I don't have a two-phase liquid. I have a one-phase liquid. And the composition of that one-phase liquid is still XA2. Then I continue to heat it up to T3. Now at T3, I have my my one-phase liquid of composition that I see right there, XA3, but now I begin to get vapor. And to find the composition in the vapor phase, I slide along the tie line and note that the intersection of the vapor phase curve is at composition way richer in A, and as a matter of fact, that's a value XA3. Now, what will happen as I continue then to cool this vapor that comes down? From there, it's going to get richer and richer in A, but will be minimized when it reaches the azeotropic composition. At the if I go to the temperature of the azeotropic point, notice there's a point of intersection there for all three phases to be in equilibrium. And that will be the point where I have the intersection of all three phases. I will have vapor in equilibrium with A and B. There's an azeotropic point here where that will be. And that will have temperature TAZ along for that value. And it will have, if I go straight up the isopleth to the point of intersection of all three of those, I can have an XAZ as well. That will be a single point, no degrees of freedom. The composition, temperature, and pressure are set for those conditions. Now, okay, notice that if I continue to cool my two-phase liquid down, I will end up back into that two-phase component region, and I can check along the tie lines as to the relative composition of A1 and A2 in those phases when I come back down to a temperature like a T4 that I have on my graph. Down at T4, I can again take my temperatures along the tie line. The tie line is the horizontal line connecting the two, and I get my two-phase liquid composition at the blue dots I have placed on the curve. Those will be my XA in the rich phase, XA1 and XA2 will be my composition. I put double primes on the XA2 double prime there, as you can see. Let's look at the appearance of a two-component liquid-solid phase diagram, where again, we'll begin with the simpler regions where we have the maximum degrees of freedom. Again, two components, C is 2. We have one phase zones where we have a liquid that is mixed together, melted states of these solids in the liquid state. And it's a one-phase solid. It's not a two-phase solid. And we also have a mixture of the solids that we can mix together, and we get a one-phase solid mixed together. Very typically, it's done by melting it, stirring it up, and then letting it come back down and solidify. When you do things like that with brasses and things like solder and stuff of that sort, bronze, we are mixing various components of metals together to make a one-phase metal of them. We typically take them to a temperature where they homogeneously mix into the liquid phase and then let it solidify out, and you get these one-phase solids. So in the one-phase solid zone, I have 2 minus 2 plus 2, or I have in those regions, I have F prime is equal to 2 in those regions. Because I had an F equal 3, I'm going to again choose the pressure, let that be taken off the table. So I have two things I can vary. And again, if I do temperature versus mole fraction, I can move around two-dimensionally. I can vary the mole fraction up above the top curves or below the bottom curve. As I vary the temperature, I can move up and down or left and right. Now, if I'm under the middle curve, I'm under the top curve, but above the bottom curve, I'm in a so-called two-component, two-phase regime. And my two phases there are liquid mixed with solid. But in this case, you'll notice a tie line connecting the liquid-solid regions either goes all the way over to the pure A axis or the pure B axis. So in the left hump, under the left hump, I'm in the regime where I have liquid in equilibrium with pure B. Under the right hump, liquid in equilibrium with pure A. And a tie line at a given temperature will tell me, of course, I have pure A or pure B, but the liquid in equilibrium with them will have different compositions. Notice when I have pure B, my liquid will be richer in A. When I have pure solid A, my liquid will be richer in B, as you might expect. Now, there is a magic mixture here, much like we saw in the liquid vapor that we called an azeotrope. Here, however, where we have the magic mixture of liquid, with liquid with solid, we call that the eutectic mixture. So there's one eutectic point, which is the lowest, as you will note there, the lowest melting point of the solid is the eutectic melting point of the solid. And when we will melt the eutectic, it melts without change in composition. As we will see when we melt other things, there's going to be change in composition with different mixtures, and that will head towards the eutectic, as we'll see on the next slide. This slide examines the ramifications of preparing a sample that begins with mole fraction that we see here, YA. So I prepare a sample of a mole fraction YA. And at first, it's at low temperature, and it will be in a one-phase solid regime. When I heat it up to a certain magic temperature, TE, the first appearance of liquid occurs, and that liquid will begin to have composition of the eutectic mixture. Now, above the eutectic temperature, like for instance, when I get to T1, I can put a tie line across from the YA isopleth, and I can intersect the right axis, which tells me I have some pure A present, but I have also a bounce over to the left side that tells me I have liquid in equilibrium with pure A. The liquid has no, the solid has no B in it. I'm in equilibrium with pure A. So all the B has melted. All the B is in the solid at that point. Now there is A up in there as well, and the mole fraction of A in the liquid can be found using the tie line, and I can go across from YA at T1, at the tie line T1, hit the liquid solid interface line and come down and find that the composition of the liquid at temperature T1 in terms of A is XA1. If I continue to heat it up to T2, I go make a tie line, a horizontal line straight across. I'm still underneath the liquid solid in equilibrium curve. I'm still in the right side curve of that. I can put a tie line, of course, across and find XA2 is the liquid composition mole fraction of A at temperature T2. Now at temperature T2, the liquid has all of the B dissolved in it. All the B is up there. The solid is only pure A in equilibrium with that liquid that has mole fraction XA above it. Now, as I continue heating up to T3, then I will melt the entire sample, and I can just continue upward from that point, and it will have the original composition for the liquid above that point. Let's prepare a bunch of different mixtures of two solids. Let's heat them up until the entire solid melts, and let's begin to let them cool. So what will happen is, as they cool, the compositions will fall along the vertical line we call the isopleth. So I'm going to come down the isopleth from high temperature when I'm in the one phase liquid region, and I'm going to fall straight down along curves E, 1, 2, and 3. So let's start by falling along curve E, which of course is the eutectic composition. Whatever mole fraction I put in there is the eutectic mixture. I'm coming right along the E curve and hitting the so-called eutectic point. The eutectic point, again, is a triple point. There are no degrees of freedom at the eutectic point. At that point, I have liquid in equilibrium with pure A and with pure B. So there are no degrees of freedom remaining at that point. So there's a fixed temperature, and A and B pure, along with the eutectic mixture of the composition of the liquid. Now let's look at the curves. Let's look at the appearance of what a curve would look like with temperature versus time as I cool these samples. Look at the E curve to the far right. I have a diminishing temperature with time. It looks like a nice linear function of temperature with time until suddenly I come to not an inflection, but actually a discontinuity in the curve. It bends over to the right. And notice at that point, I have no decrease in temperature for a long period of time. What I'm doing there is this is the latent heat of melting point heat of changing phase or fusion point, if you like, of the liquid to the solid. This is the temperature of fusion of the eutectic mixture, and I have no change in temperature while that's occurring because it's a exothermic process of heat being released as the materials change from liquid to solid, so there's no ability for the temperature to fall at that point. We call that the eutectic halt. The eutectic composition has the largest time of the so-called eutectic halt. Now notice after the entirety of the eutectic mixture has solidified, now I can go again after a discontinuity to cool the solid mixture of composition E. And that's a nice linear function, diagonal line showing cooling the solid. All right, now let's go over to curve number 3, the next one over to E. This, you will note, by composition has the minimum amount of A compared to the amount of B. So that's has the XA3, the smallest of the remaining compositions beside the eutectic. Again, when I look at the cooling curve, temperature falls nice and linearly with time, but then there's a first discontinuity. And at the first discontinuity, the pure A will begin to come out of solution first. Why? Because I'm to the right, come down along isopleth 3. As I make the tie line connecting, I come to the phase boundary where liquid begins to occur. And I make the tie line, it hits the liquid, the liquid one component mixture and the pure A axis. So A begins to precipitate out. And again, there's a nice diagonal for that. And as that occurs, as the A begins to precipitate out, the solution gets richer and richer in B. So I move along the curve from the composition of mixture of the isopleth 3 towards the eutectic. I'm getting richer and richer in B as the mixture approaches eutectic. Now, eventually, I get to the same temperature of the eutectic halt. But notice I have a shorter eutectic halt because I have less of the mixture of the eutectic composition. Finally, when that eutectic is all solidified, then the solid can cool along after another discontinuity in the curve. I can diagonally cool the solid. Now, let's just move over to composition 2. That is richer in A than was composition 1. So when I cool the mixture of that composition, notice A begins to precipitate out sooner because I'm higher. I intersect the curve of the A beginning to appear at a higher temperature than I did for mixture 1. So A begins to come out at a higher temperature than it did at 1. The discontinuity on the cooling curve for that solution 2 is higher than it was for solution 3. And notice that the part of that curve is longer till I reach the eutectic because I have to come along the composition towards the eutectic. Or as more and more A comes out of solution, it gets richer in B and richer in B, and I'm moving towards the eutectic. Notice there's a shorter eutectic halt for composition B because there's less time or there's less amount of the eutectic present when I finally make it to the eutectic point along that cooling curve. Then finally, I look at cooling curve 1, which is which I have, in that case, the most A present. So there's a discontinuity where the A begins to precipitate out. Notice A has to precipitate out the longest period of time before it reaches the eutectic amount of A present. There's the shortest eutectic halt for that particular curve because there's a minimum of the A present after there's a minimum of that phase present because of the massive amount of A that's already precipitated out. So the eutectic halt is shortest for that one. And finally, when the eutectic has entirely melted, then I can cool the two-phase or the one-phase solid after I get below the eutectic point.